Welcome to Game Theory Simultaneous Games Part 3. In this lesson, I'm going to talk about mixed strategies. For some games, it's advantageous for some, if not all, the players to use a mixed strategy, which involves playing each pure strategy according to a probability distribution. So we saw this for the rock, scissors, paper game, where we speculated that it would make sense for each player to play each pure strategy 1/3 of the time to keep their opponent off guard. And these are the general um, assumptions for these mixed strategy games. The game is played several times, so we saw again the rock, scissors, paper game. The idea is you don't just play that once. There's no dominant strategy equilibrium and no pure strategy Nash equilibria. So we saw an example of this towards the end of the last lesson, and we'll come back to that. And it's beneficial to keep your opponents guessing. So if you keep playing the same strategy, if it's uh, in a game like rock, scissors, paper, you're going to eventually pretty quickly, your opponent's going to see that, and then you'll start losing all the time. So you need to keep your opponent off guard. So that's the idea of this, playing these different strategies based on a probability distribution and randomly. So you don't want to play, 5 times rock and then 5 times scissor and 5 times paper and then continue that. Even though that's 1/3 of the time for each, it's rather not random at all. It's a predictable pattern. So you want to avoid that also. On this slide, I analyzed the pitching pennies game from the perspective of mixed strategies. And just one clarification that may help. I realized that the pitching pennies, the players don't have a choice as to whether it's heads or tails, and that makes this a little bit awkward fit for the game modeling that we're doing here. So why don't we shift it a little bit, and let's say that the players are playing online, and player A and player B get to pick either heads or tails. They put that into some type of secure system, and then the two selections are shown to the two players, and then they proceed as they would have if they were pitching the pennies. In other words, if you have a match of two heads or two tails, effectively A would get more, would have 3 points, and B would get 1 point. And if they don't match, if you get a tail and a heads based on the selections of players A and B, then B would win in that case. It would get 3 points to A's 1 point. Okay, so what we're going to do here is define two more strategies. They're mixed strategies. Sigma sub 1 is the strategy where player A randomly selects tails 50% of the time and heads 50% of the time. And strategy sigma sub 2 is similar for player B, where player B selects heads 50% of the time and tails 50% of the time. And what we can do is compute the expected payoff for we'll start with player A. If player A uses strategy sigma sub 1 and player B always pitches heads. So in that case, the expected payoff would be 0.5. In other words, A is doing half and half here with tails and heads. So it would be 0.5 times 3 plus 0.5 times 1. That would give us 2. And then for B, it would be 0.5 times 1 plus 0.5 times 3 would be 2. And then if player A uses strategy sigma sub 1, but B always pitches tails, in other words, this column here, then we can also compute the expected payoff for A and B. And it's almost the same thing, except the numbers are shifted here. So you have 0.5 times 1, that's this one here, plus 0.5 times 3, you get 2, and then 0.5 times 3 plus 0.5 times 1, and you get 2. So player A is indifferent as to whether player B chooses heads or tails, since in all cases player A gets, or should I say both cases, player A gets 2 points. And it's completely symmetric. Player B has the same lack of concern as to what player A is doing when player B uses this strategy, sigma sub 2. Okay, let's continue with the analysis on the next slide. So I have here the table from the previous slide, but I just inserted the two additional strategies, the mixed strategies, sigma sub 1 and sigma sub 2. And what we computed on the other slide were this payoff and this payoff, and this payoff here and this payoff here. Or at least we computed these two, and then I mentioned that it's symmetric and you would get the same thing for B. And what we haven't computed is this one here. If both players use the mixed strategy, sigma sub 1 and sigma sub 2, but we can compute that up here. When both players use mixed strategies, the expected payoff for player A is if there are two heads or two tails, player A gets 3, and that happens 25% of the time. So that's this term and this term. And then if the outcomes do not match, heads, tails, tails, heads, A gets 1 point, and that happens 25% of the time, or 0.25, and so you get 2. And since it's a symmetric game, it's the same result for B. So we get 2, 2 for B here. And the next step is we look for the Nash equilibrium in this case. If you recall, when we did it the first time and we went through that analysis, we just had this 2 by 2 matrix here, and we put the little stars in the appropriate places, and we saw there was no star in both entries for any one of the cells. So we concluded there was no Nash equilibrium based on pure strategies. But now we have these mixed strategies, and if we do the analysis, in other words, if we look for the best choice for A, given when B plays heads, we see that the best choice would be 3, so we put a star there. And then the best choice for A when B plays tails would be 3, so it would be this one. And then when B plays the mixed strategy, it's the same. So we put a star next to all of the 2s here. Then we can do the same thing for B. So when A plays heads, the best choice for B is this one, this one here. So we have a star next to the 3. Then when A plays tails, the best choice for B is here. And when A plays the mixed strategy sigma sub 1, it's 2, 2, and 2. So we put a star next to all of these. But now you see what we've done. This cell here to the bottom right has a star next to both of the entries. And so this is now a Nash equilibrium, but it's based on these two new mixed strategies that we constructed for the game. All right, let's look at another example. So we had the same problem with the rock, scissors, paper in the sense that we did not have a Nash equilibrium. That was this 3 by 3 matrix that I'm pointing to in here. When we did the analysis, you notice we did not get a star next to both elements in any cell. But we can do the same thing we did with the pitching pennies. We can create two mixed strategies. And as we discussed in previous lessons, the idea would be to play each one of these a third of the time randomly. So we'll have sigma sub 1 be that. In other words, A would play rock a third of the time, scissors a third of the time, and paper a third of the time, making sure that that's done randomly. And then we have the same similar strategy for B. So I put those in our matrix and I extended our matrix. And then we can do the analysis to find the Nash equilibrium. So if we look at the best choice for A when B plays rock, it's this one here. And then we can continue, it's here, here. And then when B plays strategy sigma sub 2, the payoff is 0, 0, 0, all the way down for A. So we put a star everywhere here. And I should probably explain the expected payoff. It's pretty much what we did in the previous example. I won't go through all the details, but let's just look at one of them here. So if B plays rock, the expected payoff for A, if A plays sigma sub 1, is 1/3 times 0 minus 1 times 1/3 plus 1 times 1/3. And so these just cancel out and you get 0. And it's the same doing down all of these and going across for B. You're going to get 0 expected payoff in every case. Okay, but in this case, when we do the Nash equilibrium analysis, just like we did in the previous example, we get a star next to both of these entries here. So this is actually the Nash equilibrium for this extended problem here was the two mixed strategies. Okay, so you may wonder if that always happens, and I have a theorem on the next slide that addresses that. So in fact, we have this theorem. Every game with a finite number of players, each of which has a finite number of pure strategies, has at least one Nash equilibrium, which is possibly a mixed strategy. So we saw that in the last two examples. This theorem was stated and proved by John Nash in his PhD thesis, 1950. And of course, that's why it's called the Nash equilibrium. Then we have this caveat here, and I'll address this in the following slides. For the pitching pennies and rock, scissors, paper games, we were able to guess the mixed strategy equilibrium given the high level of symmetry in the payoff matrices. So we guessed 1/2, and rock, scissors, paper 1/3, 1/3, 1/3. But sometimes you actually need to do some calculations to figure out the appropriate mixed strategy. And I'll show you an example of that as we proceed through this lesson. In this example, we need to calculate the percentages or the probabilities for the mixed strategies. Unlike the previous two examples where we were able to just look at the example because of symmetry and decide what the probabilities are. So here we have the game. You have player 1 and player 2. Player 1 can do strategies A or B. Player 2 can do strategies X or Y. And these are the payoffs. And if we do a Nash equilibrium analysis on this alone, we see that there's no dominant strategy because if you look at player A, A does better with, player 1 does better with A when player 2 plays X. However, when player 2 plays Y, player 1 does better with B. So we put a star here and here. And then if we look at player 2, when player 1 plays A, player 2 is better going with Y, so we put a star here. And then when player 1 plays B, player 2 is better off going with X, so we put a star here. And as you can see, there's no 2 stars in any one of the cells. So there's no dominant strategy for either player, and there's no Nash equilibrium. So we go to the next step, as we've done before, and we define mixed strategies. So we'll call the mixed strategy for player 1 sigma sub 1, and that involves playing A P percent or P proportion of the time, And then, of course, B is being the only other option would be 1 minus B. So these two have to add up to 1, right? There's law of total probability. And we want to make this probability such that player 2 has no preference in playing X or Y. There are two strategies. One player 1 plays the mixed strategy, sigma sub 1. And then we do the same thing for 2. We just use Q instead of P. So unlike the other examples, the probabilities could be different for the two mixed strategies. And in fact, they are. You'll see when we compute them. Okay, so let's do the computation for this one first. If player 1 employs sigma sub 1 mixed strategy, then player 2 has a payoff. You can see here it's 1 times P plus 3 times 1 minus P. So that would be the payoff when player 2 plays X. And then if player 2 plays Y against player 1 still playing sigma sub 1 strategy, then it would be 4 times P, this term here, and then plus 1 times 1 minus P. And we want player 2 to have no preference between playing either one of these strategies against player 1 playing sigma sub 1. So we want this to equal this, which is what I've said here. And then we just solve for P. Okay, so we get P equals 0.4 and 1 minus P equals 0.6. So we know what sigma sub 1 is in terms of mixed strategies. And then I'll go on to the next slide and we'll do the same analysis to find the probabilities for sigma sub 2. Okay, so now we're looking at if player 2 plays sigma sub 2, we want to have it such that player 1 doesn't care whether he or she or it plays A or B. So we compute the two different outcomes. So player 2 plays sigma sub 2 and player 1 plays A, and then you would get 3 times Q, this term here, plus 2 times 1 minus Q. So that's the payout for player 1 given strategy A against strategy sigma sub 2. And then we go down to the other option. If player 1 plays B, then it would be 0 times Q. So we don't even have a first term. And then plus 3 times 1 minus Q. That's this term here. So these two. And then again, it's just basic algebra. We solve for Q and we get Q equals 1/4 or 0.25. 1 minus Q is 0.75. So now we have the probabilities for the sigma sub 1 and sigma sub 2. And I didn't do all the calculations here. I just showed you the final results. Maybe we can look at one here. So we'll look at the payoffs. If player 2 plays X and player 1 plays sigma sub 1, then the payoff for 1 is 0.4 times 3 plus 0 times 0.6. It's 1.2. And then at the same time, 2 would have 1 times 0.4 plus 3 times 0.6. So that's 1.8 plus 0.4. That's that one here. All right. And then we do the same thing here. We get these values. Then we do the computations this way. If player 2 plays sigma sub 2 and player 1 plays A, we can calculate those payoffs and then these payoffs. And then we have everything except this here. Then we have to compute the expected payoff if player 1 plays sigma sub 1 and player 2 plays sigma sub 2. and we can do that. We've done that before. There's several calculations. We need to use all these probabilities here to come up with this. I'll leave that as an exercise for you to verify. And then the last step, the punchline, right, is we want to verify that we have a Nash equilibrium. So we go down each row. So what's the best play? If player 2 plays X, what's the best strategy for player 1? And that would be 3. So we put a star there. Then we come here and we say if player 2 played Y, what's the best strategy for 1? That would be 3. So we put a star here. And then the clincher is here. If player 2 plays sigma sub 2, then you have the same payout in all 3 cases for player 1. I mean, we designed it to be that way. So we have a star here, here, and here. Then we do the same thing going for if player 1 plays A, the best strategy for player 2 is 4. Player 1 plays B, the best strategy for player 2 is 3. And if player 1 plays sigma sub 1, again, by design, player 2 doesn't care. It can play X, Y, or sigma sub 2, and you get 2.2 in each case. So we put stars there. But now you see that we have a star in both cells. And so this is the Nash equilibrium. We have player 1 playing sigma sub 1 and player 2 playing sigma sub 2. And these are the respective payouts. Okay, so quite a bit of calculation there. And this is only a 2-player game with only 2 pure strategies. And then we had to develop these mixed strategies in order to finally get a Nash equilibrium. So I was going to leave this as an exercise, but I decided to show the computation of the payoff when player 1 plays the mixed strategy and player 2 plays the mixed strategy. So first, to do this, we compute the probabilities of the occurrence of these 4 strategies, AX, AY, BX, and BY here. And since the players decide independently, we can just multiply the probability of X times the probability that A is going to be selected by player 1, and that's just the 0.4 times 0.25. We get 0.10, and we do the same for the other 3 cells here. And so we have the probability of each one of these strategies being used under the mixed strategies, right? These probabilities all relate to the mixed strategies. And so we want to use these to compute the payoff for, well, first we'll do it for player 1. So player 1 has a payoff of 3 times the probability of this combination happening, AX, so it's 0.1 times 3. And then the probability of A and Y happening is 0.3, and we multiply that times the payoff for A here is 2, then 0 times 0.15, and then 3 times 0.45. We add those up and we get 2.25, and that's what goes in here. Then we do the same thing for B, except we're just working on the second component here. So it would be 1 times 0.1 plus 4 times 0.3 plus 3 times 0.15 plus 1 times 0.45. These terms here, and you add those and you get 2.2, and that goes in here. Okay, so this is the payout, the expected payout if player 1 and player 2 play these mixed strategies. And the shortcut I've listed here goes as follows. Let me just read it to make sure I get it straight. The strategy sigma sub 2 was constructed to make player 1 indifferent between A and B. In other words, these payoffs are the same for player 1, right? 2.25, 2.25. And since the strategy sigma sub 1 is just a mixture of A and B, percentage of each, and the percentage adds up to 1, right? It's 0.6 and 0.4, or should I say 0.4 of this and 0.6 times this, and of course you're going to get this number here, and then the same argument going down this row here, you're going to get 2.2. So the upshot is you can just compute the payouts for these two cells and these two cells, and then you can just read off the second component is the same here, and then the first component of these two is the same as the first component here. On this and the next few slides, I want to talk about a weaker condition than the Nash equilibrium. It's called rationalizable, and I have a definition of it up here. A strategy that survives the iterated elimination of strictly dominated strategies, which we talked about in the previous lesson and we abbreviated as IESDS, is said to be rationalizable, noting that mixed strategies can be used to eliminate other strategies. Okay, so if you can survive this IESDS, the strategy is said to be rationalizable. In terms of relationships, a Nash equilibrium requires everyone's belief to be correct. Each player's strategy is a best response to the strategies the others are actually choosing. Rationalizability is weaker. It requires only that each player's choice be defensible under some internally consistent belief about rational opponents. So we're going to prove a theorem related to these two concepts in the next slide. And what I have here is just to remind you some of the definitions. I would have fit them on the same page as the theorem, but the proof of the theorem took the whole page. So you may want to do a screen capture of this paragraph here just so you have to look at when you see the theorem and the proof on the next slide. Okay, so again, as a reminder, two definitions are used in the proof when we've defined these things before. Recall a strategy S sub I is the best response to the opponent's strategy, this S with the not I, if the payoff for S sub I and the strategies of the opponents is greater than or equal to the payoff using any other strategy available to player I, whether pure or mixed. So that's known as the best response. Second, at a given round of the elimination process, and we're talking about this here, S sub I is strictly dominated by sigma sub I if the payoff for sigma sub I and any other collection of strategies from the other players is greater than, strictly greater than, the payoff using S sub I. Right, we've seen that in the 2 by when we had just two players, and then we were just looking for one row to always be better than another row for a given player, or one column better than another column for one player. But this definition is more general because you can have I could go from 1 to n. You could have n players in this case. Okay, so we're going to use these in the proof of the theorem on the next slide. Yeah, and the restriction to strategies that are all still available, referring to the second definition here. That's important. The strategy can fail to be dominated in one round and then become dominated at a later round once other strategies have been removed. And we saw that when we did some of the examples in the previous lesson. So here's the theorem. It's number 40 from my book. It's not, the number really isn't important for these slides, but just to let you know, I've copied this out of a book that I've written. So if S equals S1, S2 up to Sn is a Nash equilibrium, then S sub I is rationalizable for each I. So in our proof, we show that no Si is eliminated at any stage of the iterated elimination of strictly dominated strategies, which it follows the definition of rationalizable. So that's what we need to prove. The argument is an induction on the round number of the elimination. Note that R counts rounds and while N is the number of players. Right? There's strategy here for each player. Before any elimination takes place, every strategy is available. So each SI is available at round R equals 0. This is the base case for the induction. So our induction hypothesis assumed that S1, S2 up to Sn are still available at round R. In other words, at the beginning of round R before we've done another elimination. Now fix a player I and suppose that S sub I is strictly dominated at round R by some strategy, sigma sub I, that is still available. By the definition of strict dominance, the payout for sigma sub I in conjunction with every other opponent profile, T sub naught I, is greater than the payout taking S sub I with every other opponent profile, T sub naught I. That is available at round R, referring to these T sub naught I's. By the induction hypothesis, the opponent's equilibrium strategies, S sub naught I, are still available at round R. So we can take the T sub naught I equal to the S sub naught I. In other words, it's all these strategies other than S sub I, which gives the payout of sigma sub I, S sub naught I, greater than the payout of S sub I, S sub naught I. However, S is a Nash equilibrium, right? That was the assumption. So Si sub I is the best response to S sub naught I. That gives the payout of S sub I with S sub naught I greater than or equal to the payout of sigma sub I with S sub naught I. So we have two contradicting inequalities. Therefore, no sigma sub I exists. S sub I is not strictly dominated around R, and S sub I is still available at round R plus 1. Since we took any player here when we started, player I was chosen arbitrarily, so all S sub 1, S sub 2, all the way up to S sub n survive around R plus 1, and that's what we needed to prove by our induction. We assumed it up to R, and then we proved it for R plus 1. So by induction, each S sub I survives every round, hence each S sub I is rationalizable. On this slide and the next, I have a counterexample to the theorem from the previous slide. So consider the game in the table below. This is one we've seen already. So S11 is the best response to player B playing S21. This here, right? But since player 1 then receives 3 rather than 1 here, however, S12 is the best response to player B playing 2-2. So in other words, neither one of these strategies dominates the other for player 1. And this being this symmetric game as it is, we have the same situation for B, that this strategy for B does not dominate this and vice versa. So by the consequence noted above, none of these 4 strategies is strictly dominated. Allowing mixed strategies to do the elimination does not change this. You can see that here. This, if you look at the bottom row here, that does not dominate. Dominates here, but then not here. So this 3 is better than the 2, and the same issue with the first strategy up here. So the IESDS, in other words, this elimination strategy process removes nothing, and all 4 pure strategies are rationalizable. Okay, and that's this one, this one, this one, and this one is what's referred to here as the 4 pure strategies. Okay, so the theorem does not hold in the reverse direction, as we'll see on the next slide. So we have all these 4 strategies being rationalizable, but as we know from looking at this example, and I'm kind of giving away the punchline, but we know that there's no Nash equilibrium for these at least pure from out of the pure strategies. We do know there's a Nash equilibrium out of the mixed strategies. So let's continue on the next slide. So just to finish this off, now consider this strategy profile S11, S21, this one here. And we could have considered any one of these for both strategies are rationalizable. However, the profile is not a Nash equilibrium. Right, we've done that analysis already. It doesn't have the 2 stars next to it. And we could have done it for this one, and this one. So in fact, this game has no Nash equilibrium in pure strategies. Each of the 4 pure profiles gives one player a reason to deviate. The only Nash equilibrium is the mixed strategy profile, this one down here, which we saw before. So by the previous theorem, sigma sub 1 and sigma sub 2 are rationalizable, but these are mixed strategies. Hence, rationalizability is a weaker requirement than membership in Nash equilibrium. Every equilibrium strategy is rationalizable. So this one here, these sigma sub 1 and sigma sub 2. And this example shows that the reverse does not hold. All 4 of the pure strategies, these 4 in here, are rationalizable, yet none of them belongs to a Nash equilibrium. Okay, so that was it for this lesson. I have another lesson on the minimax theorem. And then I have a few lessons, probably 1 or 2, on sequential games. You remember the trees that I had earlier in a previous lesson where one player decides and then another, based on that, the second player or however many players you have decides, and then you continue on in that pattern. So that's a sequential game, and I have some lessons I plan on that also. Okay, so if you like this, please give it a thumbs up and stay tuned for further lessons.